Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you so much, Anna. Hello, everyone. Good morning, good afternoon, and good evening. Welcome to the AI for Good Machine Learning 5G Challenge webinar session. My name is Thomas Baskol from the ITU. I would like to welcome you all for joining the session. The Machine Learning in 5G Challenge aims to create a community to solve network-related problems. And in today's session, will be given by Professor Walid Saad. He's a professor at the Department of Electrical and Computer Engineering, Virginia Tech. In this talk, he will provide an overview of two use cases, as well as shed light on how distributed machine learning can be a key enabler for the design, deployment, and management of future wireless systems and their associated technologies and applications. So I would like to welcome Walid. Good morning, and welcome to this webinar. So I'll give the floor to you.
Yeah, I'm sharing my screen. Can you see it?
Yes.
Okay, so it's a great pleasure to talk in this challenge about some of our research on distributed machine learning in wireless networks. So as you can see, I have a small asterisk in the title. In the first part of my talk, I will violate my distributed angle, and you'll see why, because I wanted to build gradually towards kind of the main message. So I'll start with an introduction, and I would say the big headline would be towards generalizable machine learning in wireless. How do we get towards learning schemes that can generalize, that can actually not just mimic what they've seen in the data, but that can go beyond it. And I will talk also a little bit about edge learning as a use case of wireless. That will be a couple of slides towards the end. So I'll get more into that later. So AI, how is the evolution of AI? And of course, this is from the lens of wireless communications, but also as a general sense. So AI is very old, right? It started in the Greek island of Crete, where there was this bronze man called Talos who was defending the island of Crete, and he had some sort of AI mechanism, but it was really fiction. And today, AI is a strong computing tool, right? So it can do all sorts of computing, from arithmetic to math to computer vision and to everything we want. Now, although this is a cliche in some sense, you would hear it in every maybe AI and wireless talk. What we want to have is AI as a brain, right? So it can mimic some of the features of the brain. So what that means can be a little bit fluffy. So I will try to make it a little bit more concrete in this talk and kind of tell you where we're getting at, right? So what does that mean, at least for us in the wireless domain and so on. So looking at a bit of a contrast of AI, today's AI in general, and what we like to have. So most of current AI are centralized. Of course, federated learning has emerged recently, and that's a big thing that's moving us here. But in general, mostly they're centralized single agent at the controller. And we want to have multi-agent. So people would say, when they say distributed AI, they talk a lot about federated learning, right? And I will talk about it a little bit towards the half of this talk. But it's not the only thing. It's really multi-agent that we care about in communications, right? Because at the end, we're in a communication system, we're not looking primarily to protect privacy, although that's very important. But when we want to do, let's say, a resource management, an AI-native resource management scheme, what we care about mostly is that there will be multiple agents who can actually control that scheme. And of course, privacy would be very important to have, but that's not really our main motivation. Second is, of course, big data has been the norm. Now we look more at small data that's kind of fractionally distributed across the system. And in the past, and in current AI, it's often either you have a model-based system or a model-free system. What we want is what I can group under explainable system. Think of it as a model-aware system. It still is model-free, but can use some priors from the rigorous models we have to actually improve its performance. A lot, and the big challenge is perhaps on the training side, right? So today's AI is very training dependent, and we're hoping to get to a point where it's training free. And that kind of loops into the last point, which is the one I will hit on mostly in this talk. It's current AI algorithms, they learn specific tasks, right? I can optimize the resource blocks of a sub 6 gigahertz or FDMA system. But in reality, what I want is to learn a skill. I need to learn a class of optimization problems, not a simple one, right? I need to be able to also generalize to environments that I haven't seen or tasks that I haven't seen. Some people call that reasoning because it relates to the brain, but in reality, it's really about generalization, right? How do you generalize to unseen events? How do you effectively generalize? And also there's reliability is an important aspect in the sense that existing ML tools are inherently not very reliable because when they see unseen tasks, they either have to retrain or they have to do some tricks in order to kind of learn those tasks. And while that is okay in a computer vision environment, in a communication system, we need rapid, fast, quick decisions. And that's not great with some of the existing tools, like reinforcement learning, for instance. I'm going to talk more about that. So I will focus on these three factors, even though we've been working on all of them, but I will focus on these three factors in this talk. And in two angles, I will look at how learning helps to communicate. That will be a big portion of the talk. And at the end, I will talk a little bit more about how communication systems help enable like federated learning in other algorithms. So let's start with, as I mentioned, this first part a little bit is not distributed, but it kind of fits on the other aspects. Let's start with this idea of brain-like AI, right? One of the key factors of the human brain is the ability to get experience. If we get experience, the more we get experience, the better we are at a given task. So this brings us to our first work, which we call experience deep RL or deep reinforcement learning. And the key goal was to make the communication more reliable. So the system model is, it would be very, very traditional, but as a motivation, as you know, URLLC is an important staple of 6G and so on. It has been around for a while, but there are some drawbacks in existing works. One, they mostly talk about short packet uplink, but that's not really what we want. We want to look at broader applications like VR, like vehicular networks, like drone control, which are not necessarily uplink, not necessarily small packets, not necessarily sensitive, but still they want to be reliable and they want to be low latency. Second, they assume typically known models, and this is one motivation to use machine learning because when you're modeling latency and reliability, having models like Poisson arrivals and things like that are not great because they kind of are approximations at the end. So model free is very appealing, but I'm going to talk about how we go beyond what's been done. So deep RL is useful. So many people have said, well, we need model free, so we use deep RL. That works well if you're doing network slicing for EMBB, let's say, applications. But if you want to look at, again, by URLLC, I'm using it in a loose term, not uplink short packet. It's more like reliable communication. So learning in a reliable communication environment must handle extreme cases, like a rapid surge in traffic or a rapid change in the environment. And unfortunately, deep RL is not equipped to do that, especially in the current existing algorithms. So how do we make it more generalizing? How do we make it more effective? So I'm going to talk about experience as a key. And the answer, the question I'm going to ask is, can we design a reliable RL or AI in general, but reliable RL in this case, that can work well under extreme conditions to achieve URLLC or more broadly reliable links, reliable communication links. So the system model, as I mentioned, is simple. I'm going to give you a simple problem to start with. So it's a downlink single base station communication system that's sending latency sensitive messages to either vehicles or VR or whatever. I mean, the application is not very specific in my model. It's OFDMA system, so you have a downlink data rate that depends on the resource block allocation. So RB is the resource block allocation indicator, the bandwidth, and the K is the number of channels. This is the channel gain, and this is the power. So this is just the Shannon data rate. Okay, so the bandwidth is B. So the key is to looking at reliability. So the reliability is typically defined as the probability of the end-to-end delay exceeding the threshold, right? So you want to keep it below a threshold to be reliable. So we can map it to this. I mean, loosely speaking, it can be mapped to this constraints where you kind of want your rate to be greater than some function of the arrival rates. Let me show the variables of the arrival rates lambda I, of the packet size beta, of the reliability gamma, which is what we want, and of DI max, which is some target latency. This is a loose relationship we don't know. We want to learn it, right? And it should be greater, of course, than the arrival rate and the packet size. So without making assumption for the delay here, it's very obvious that if we don't use a model, we need some model-free algorithm. And that, of course, motivates reinforcement learning strongly, right? So we do need that in this case. So the problem formulation, and again, while this approach is not restricted to this problem, but it's a good way to understand it. So the problem formulation is the following. It's we're trying to minimize with respect to power and resource block allocation. So we're doing a resource block allocation problem. And we're trying to minimize the total power allocated over the number of users n over time, over the number of resource blocks k, such with constraints on the reliability, which is the key thing here. We want probability of the I greater than the I max, it'll be less than 1 minus gamma I star. Gamma I star is my target reliability, right? So if you want to talk about the 5 nines, this would be the 0.0001, right? So this would be the reliability I'm targeting. We have a rate constraint and we have a power constraint and of course a feasibility. So these 3 constraints are traditional. The key is here. Now in traditional works, if you have a model for the delay, you can use Lyapunov optimization, transform this problem and create something else. But that goes back to a traditional protocol, a 3GP protocol, right? Where you have a heuristic that solves things. What if we want to use an AI algorithm, which actually learns all this, right? It tries to learn the optimization problem, not just use some iterative techniques, okay? So this is challenging to solve because I don't know this equation, right? It's not easy. It has to be data-driven. So to handle it, we can first think a little bit more carefully. How can the network measure reliability? In some sense, he can measure it using this kind of equation. So it's 1 minus this reliability constraint, which is nothing but 1 minus the ratio of the number of packets that exceed the delay divided by the total number of packets. And this ratio itself is something measurable, which means it could be data-driven, right? It's measurable. So we can actually learn it and work with it. So this is clear. Reinforcement learning is very natural here. But classical solutions have a problem with large state space that has been resolved with DeepRL. But DeepRL also has its own problems. It cannot handle large action spaces. So remember, it was created for DeepMind where they go left, right, up, and down. Here we have to have a lot of resource block allocation vectors. Second, it's not reliable. And I'm going to see how to handle these two. So this is our general framework. You have a DeepRL algorithm that uses policy, proximal policy optimization to determine the target rate. Then once we find the target rate, we create something using optimization called action space reducer. So this is one of our contributions. I'm not going to go through it too much. It's just a way to simplify the optimization problem, okay? And it uses optimization techniques. This is how we reduce the action space. And then you go to the system end to end, you measure, you take a reward and go back, right? So defining the reward function comes from my optimization. It's function of the reliability, function of the total power, with a weight here that controls your reliability. So this weight allows me to control how far or close to the reliability constraint I am. And we can show mathematically, oftentimes when we do RL, we say, oh, it's hard to prove things. No, we can sometimes prove things. So here we can prove that, well, after convergence, if you use this reliability, you guarantee that the users have guaranteed the reliability constraints. Of course, this is contingent on the problem being feasible, right? If you don't have enough resource blocks, then there's nothing I can do. But assuming the problem is feasible, then you can achieve the reliability. Now, the action space reduction, I'll be very quick about it. So again, it's just a technique that we use based on optimization. So we use a two-step. First, instead of optimizing over RB and power, we optimize over rate using PPO. And then we reformulate the problem and show that with a very low error in approximation, 1% or 2% at most, we can have a much faster, nearly polynomial time solution without having to go through a lot of actions. But my really main question is DeepRL suitable for reliable communication? No, because the problem is when you run it, if it sees a new environment that was not in the training, and that is very important in reliable communication, because by saying we are reliable, it means we have to be reliable against these extreme events, right? So it could be very slow to adapt to it, but I mean, this violates our main issue, which is I want to be low latency, I want to be reliable. So I introduced DeepRL to actually solve the problem, and then DeepRL itself is not reliable and is not low latency, right? So how do I resolve this kind of dilemma? So one solution that we propose here is this idea of experience, and it leverages the idea of GANS, generative networks. What is a generative network? I'm sure probably many of you know it better than me, but just to be brief and quick from Ian Goodfellow's definition. So it's basically a basis of two neural networks, a generator and a discriminator. The generator tries to generate some samples in a way to eventually fool the discriminator and make it unable to distinguish between real and fake data. The simple example is this deep fakes and other algorithms that generate fake celebrity photos, right? So what they can do is they can tweak these two neural networks in a way to work well. So of course, it has been studied before, and it has been shown that this is a zero-sum game, so you need game theory to study it, and it has an equilibrium and things of that sort. But GAN has been traditionally used to generate fake data, and there are a lot of flavors for it. How we use it is somewhat different. What we say is, well, one of the solutions to improve the training of DeepRL has been to train it offline. But realistic data, which is scarce but real, with abundant data, which is synthetic but could be, might not be as accurate as conforming to the real world, while also being able to control ourselves the generation of points that don't exist, right? That points that may be faced in the real network, but they don't exist. So to do that, what we do is we create a virtual environment that is offline, where we use GAN, and I'll tell you in the next slide how, to generate new information that is combining the real data and the synthetic data. And that allows us to control our data augmentation and our experience generation, at the same time being able to conform to real data. And then, of course, then you can deploy the DeepRL agent in an actual environment. This is to the right. So in this, we go back to an original work by Apple in 2015, I guess. They had something called the GAN-based refiner, and they faced a similar idea like ours, but a little bit different as well. They don't have reinforcement learning there. But what they said is we can generate synthetic figures of eyes, but we would like those eyes to be looking in different directions based on unlabeled real images. What they did is they came up with a refiner GAN that takes as input synthetic data and unlabeled real images, which is scarce, and refine them. So if I go back to the example of celebrity photos, right, you have GANs that can generate a lot of celebrity photos. But for our case to be reliable, I'm saying that this GAN has to be able to recognize a celebrity who has blue hair, which is very rare, right? But it still exists. So what we're doing here is basically using synthetic data to come up with these examples while conforming to the real data. We do the same, but we use synthetic data based on models to generate packet arrivals, channel information. We have unlabeled data for our simulations. We got them from another paper. They shared their data online. And then we feed them to the refiner, and then we refine this information. So now I have a very controllable data generation environment. Now, in this paper in Apple, that's all they care about, generating data. Here we want them in RL. So we train our DeepRL with the refiner. And essentially now, the DeepRL will be able to have experience before it goes into the system. And this is, again, going back to brain aspect. The brain usually learns experience. And when he applies it to a new environment, he has seen it through experience. So we train it, again, I already said this, we train it using the GAN refined data. And mathematically, this is essentially, this refiner has two neural networks, a refiner and a discriminator. And you're trying to basically make your distribution of the refiner as close as possible to the input data. And you control it with an epsilon R here, right? So there is an epsilon R that is controlling how close are you to the real data or how close are you to the synthetic data. There are, of course, corner cases. If you set epsilon too small or too large, you can get too close to real, too close to synthetic, but we want something in the middle. What we can do is we can prove, again, mathematically, that the refiner cannot be trained if epsilon R is less than a certain value. And this value depends on the data set itself. So this threshold is important because it tells me now that I need to set my threshold within a certain range so that I can be properly trained. And of course, this is a lower bound, but there's also an upper bound. We could not find it mathematically. We could see it through simulations. So using GAN now, you can create any DeepRL agent. And here again, I'm going back to my title. You can have multi-agents and you can train them with different GANs. It doesn't need to be one. So some simulations, I will show you a couple of simulations. as I mentioned, we use the real data set from another paper from 2018. And the first thing you see, we compare with 3 other algorithms. The red is ours. Black is a traditional deep RL. Blue is a pre-trained deep RL with real data. Green is a synthetically pre-trained. We can see that the proposed is the best in terms of convergence. It's close to the real time, to the real data one, but it's a bit faster to converge. But the advantage we have is not here, particularly in the general convergence, but rather in the transient state. So this is the interesting figure. At epoch 100, we inserted a surge in traffic. You can see that all 3 algorithms, green, blue, and black, they took a big hit here. They had to really go down and take this like 50 epochs to adapt to this. Notice our approach nearly instantaneously adapted, and this is the key in reliability. And this is the key where experience played a major role. Now, finally, just as an interesting view here, I look at the latency target, the reliability, and the this is not the channel rate. This is not the data rate on the channel. This is the arrival rate. So how much bits per second you can handle. So you can see here that there's a nice trade-off that comes in. So if you want to have 99% reliability with 4 milliseconds, you need 4 millisecond latency, a rate of 1 megabit per second. If you want to go to 7 megabit per second, you would have 8 millisecond delay and that significantly, and 98% reliability. So that significantly takes a hit. So there's a trade-off between how much you can support in terms of arrival rate and how much you can support in terms of delay and how reliable you can be. So some open questions. So what I did here in the GAN is I was looking at the celebrity photo as a whole. You can do something called disentangled representations, where you can look like at the nose of one photo, at the eyes of another, so at portions of data, and then synthesize new data. And that's something interesting to explore. You can also extend it to the multi-agent case, how to scale. I'm going to talk about some ways to do it. One is, can we have a multi-agent GAN? That's my next topic. One is, can we have a multi-agent generalizable RL? That's my next topic. And can we look at distribution, not averages? I would refer you to my paper with Chin, my former student. I'm not going to cover this one in this talk. And we use the DeepQ network, but you can use more elaborate architecture. Again, I refer you to some of our RL architecture with Mingje Chen, my former student as well. So let me go to this question, then we'll be talking a little bit about a different problem. So essentially, can we create a distributed GAN, right? So that's a fundamental question. Turns out there's not a lot of answers to it. Even though there's a lot of federated learning algorithms, when looking at generative networks, it's not as abundant yet. So we looked at a framework, which is purely machine learning, and we looked at its application for UAVs, for channel modeling in UAVs. And I'm going to talk about both in some sense. So distributed GANs, the idea is existing GANs, including the one I presented, they assume there is a base station or a controller where you have all the data and you can generate the celebrity photos. But what if the data is distributed? So each one of us owns different things. I own photos of female celebrities. Someone near me owns photos of male celebrities. Someone owns photos of Hollywood stars, right? We want to share this and generate anything from this entire distribution. And the data is private as well. So even though I don't focus a lot on privacy, but often we don't want to share the actual data. So the question we ask here is, can we learn the distribution of the total data, the total celebrity photos, the total channel information, the diversity of channel information without sharing the raw data and without relying on a central server? Turns out in the literature, there are some distributed GAN solutions. One is very obvious. They took federated learning and applied it to GAN. And this is the first one. It's called FL-GAN. The problem with it has several issues. One, it requires a central controller. So it's not fully distributed, really. It requires a central controller. And it turns out that it also requires a generator and discriminator at every device and at the controller. So that could be a little bit of an overhead, especially if you have a controller. You have two algorithms called MD-GAN and FTU-GAN. They remove that discriminator from the central server, but they keep the central server. And here you start relying on the central server to do your generation, which is not great. I mean, in FL-GAN, you can use your own generator, but here you're going to rely on a third party to generate your data. And then MD-GAN and FTU-GAN are the same. One of them requires exchange of information between the workers. One of them doesn't. So it turns out that these are not fully distributed. They have expensive communication requirements, especially MDGAN and F2GAN. They don't allow you to have different neural network architectures. So if in a wireless network, I do have a smartphone and a vehicle and a small sensor, I cannot run a million neurons on all of them. Each one has its own neural network. This doesn't work neither with FLGAN, nor with MDGAN, nor with F2GAN. So the question we had is, can we create a fully distributed solution with heterogeneous agent? And we called it brainstorming GAN. The idea is the following. In GANs, instead of sharing the model parameters like FL does, we can share the generated idea. And this is, again, going back to the brain. When I'm brainstorming with my students, I don't share with them the pathways of my neurons. I don't know what those are. I share with them a representation of what I'm thinking, which is an idea. So this is what you can do here. The generator can share a fake data with the other agent, and that allows you to maintain some privacy. It's not fully private, right? But even FL is not fully private, so that's a different story. But you don't share the real data, but also we can show that if you do this brainstorming, you can have a fully distributed solution. No central server, and we have analytical results, I'm not showing them in this talk, which show that this multi-agent GAN has a Nash equilibrium, so we extend the algorithms of Goodfellow and so on. So we have the mathematical theory. So it's fully distributed. You can have different neural networks. I'm going to show why it's less overhead than most baselines. Even though the generated output can be larger, we can show that it's better, especially compared to most of the other algorithms in terms of communication overhead. So simulations, let's take the example I was saying. What if we start with a very simple one. I have a circle, a ring, and one user owns half the ring, the other user owns half the ring. Can they use BGAN to actually generate a full ring? The answer is yes. We can show it by simulations. So this is very simple. Let's move to a more complicated data set, the MNIST that I'm sure most of you know. What if I own digits 0, you own digits 1, someone else owns digits 9? Can we generate each other's digits by using brainstorming GAN? The answer is yes. You can see here, this one owns digits 0, but he's able to generate 3, 7, and 8. This means that if you go back to my experience, we're sharing experience. It's distributed experience now. So, and one more data set, more complicated, CFAR10. You can see again, the agent who owns airplane images can generate bird images. The agent who owns truck images can generate airplanes. So we can see it works on complicated data sets. We can also compare it in terms of performance using the Jensen-Shannon divergence. We can show BGAN is much better than all of the others, including FLGAN. So we're much better in terms of accuracy. We're very close to a standalone GAN that has all the samples, which is a really very centralized case. And using another metric, which is the FID, we can also show that BGAN is also better than the others. In terms of computational complexity, BGAN is better than MDGAN and F2GAN. You can see that directly. We depend on the data size, and it's smaller than what MDGAN and F2 use. But FLGAN, it depends. In some data sets, you have FL, the model parameters are smaller, so you have a better performance with FL. In others, you would have better performance with BGAN. So it depends. But keep in mind, BGAN is fully distributed. BGAN is better in terms of performance of accuracy, which is perhaps even more important sometimes than communication resources. So taking this into communication, I'll give a simple example. So, and before that, just a quick summary. So you can have a lot of things to this, right? You can enhance the privacy. You can use it for inference. You can have sophisticated networks. You can use it for security. We've done that before, but you can also use it for wireless. And I'm going to give an example. So take a UAV network, UAVs as base stations, and they're, let's say, millimeter wave. Every UAV has its own perspective on the environment, right? It sees its own channels, its own portion of the area. What if they want to share that without a central controller? So what they can do is implement BGAN. We show that you can implement BGAN, share these model parameters, and then we can show that you can optimize the way in which you share. So the optimal network, the optimal graph for sharing. And we can show, I mean, again, I'm going to be very brief in this one. We can show that, well, with BGAN, you can learn the entire spatial and temporal distribution, if you wish, of your area by just cooperating with other UAVs, right? Without needing a central controller. And again, we use an optimal, I mean, we find the optimal architecture. I'm skipping, I mean, again, for the benefit of time, I wanted to give you a quick overview on this one only. I can show simulations like the probability of convergence. You can see that it depends on the number of resource blocks, the number of users of UAVs I, the number of resource blocks B. The more you have resources, the faster you converge. And again, here also, the more you have users, the harder it becomes to converge because it's a more complex environment. But I mean, the main idea here I wanted to say, so you can use BGAN in different ways to create experience for a deep RL agent, or to model a system by exchanging information, to model a distribution. And this is what we do here. This paper appears in TWC, and you can see it there. So if you remember, I was saying, first step is generalize GAN to distributed. Second step is looking at a multi-agent RL, where you can generalize, again, learn a skill, not learn a task, learn a skill, a group of tasks. So I'll give you an example here directly on what we looked at. So we looked again at a drone scenario, but it doesn't have to be drones, right? We looked at this because it's a complex problem. So we said we have a number of drones trying to communicate with ground users, uplink communications, and they're trying to collect data, and the users go up active and inactive in a random way. So you don't know who's going to be active or inactive. So the problem itself, if I want to pose it mathematically, it's a trajectory optimization problem. So we're trying to optimize coverage by finding the optimal coordinated trajectory of different drones. So everyone is trying to coordinate. So the problem can be centralized, but that's not great because you can formulate it as a centralized problem, but that's really, really difficult. And it's not really solvable. In practice, it can be also formulated as a set of stochastic optimization problem. Every device, every drone is trying to optimize its own trajectory given a stochastic network, because as I said, the users are active and inactive. And that is essentially mathematically, even if you don't like game theory, that is a stochastic game. It is by definition a stochastic game. So you go from MVP to a stochastic game. Now, in a stochastic game, multi-agent RL has been a popular approach, but existing solutions have three issues. They need a large overhead for coordination. And typically you need to know a lot of information. They don't generalize. So if I learn some patterns here in this area, I am not able to extrapolate in this area, right? And they have high variance. So the solution can have a high variance. So we try to resolve these three challenges. This one is easy, just use policy gradient. It's not a big deal, but these two are the difficult ones. To solve it, I'll give you a little bit of an overview. So we start with an initial policy and value. So we use policy gradient. And then the network, I mean, the users will learn from the system, will interact with the system. Now, the key is here. What we do is we transform the stochastic game into a team game, meaning that you have one utility function that can be divided across multiple agents, and each agent views his own piece, if you want to. And this is called value decomposition. And it's a known approach, but we applied it in a different way to the RL problem we have here. So we did value decomposition, meaning we have a team problem, and then every user contributes to this team, but they don't have to know the entire information. So they only do local decisions. That is a combination of RL, game theory, and value decomposition. And then they do updates of their own policies. They select the action and they interact. And then once that has happened, they can update. This is the key point. This is meta-learning. So this is where we use meta-learning. Meta-learning allows you to update your initial policy and value based on your experience. What that means, it allows you to learn the learning parameters. So instead of just learning the task, you learn the learning parameters. Mathematically speaking, what it allows me here is instead of learning task by task, I learn a distribution of tasks. And if I see a task that is close to that distribution, I can generalize. I can be faster. I can reduce the transmission. So back to my, actually, I have them on the slide here, sorry. And it's too quick. Back to my challenges. Value decomposition reduces overhead. Policy gradient, which is not our contribution, we just use policy gradient. It enhances variance. Meta-learning, which is meta-RL, allows you to learn a skill and generalize. So these are the three challenges. We kind of solve them in a single framework. So with that said, some simulation result, we compare with an oracle that's an optimal solution, exhaustive search, a pre-trained value decomposition RL, a traditional value decomposition RL, and a classical actor critic. The IAC is a classical actor critic agent, multi-agent system. Okay, we can look at the successful service rate. So think about it as the percentage of users you are able to serve. DBS is the number of drone base stations. So you can see where meta-train is really, it has the highest, and it's very close to the optimal solution. There is no comparison between our approach and the traditional IAC, not even some special cases of our approach, where the gains are even more significant, which is what I'm interested in, not just in the performance, which is expected because we optimize better, It's in the convergence time. You can see there's significant reduction in the convergence time. And this goes back to my generalizing rapid RL, reliable RL. So what's next in AI? So I'm gonna conclude with a few slides now. So these issues of reliability generalization, again, some people call them brain, other people call them reasoning, some people call, there's a lot of terminology. All of it is fluffy for me. We need to be a little bit precise in what we're doing. The idea is the ability to give experience, to give out of distribution generalization, to go beyond standard learning and go towards this kind of more a smarter learning of skills. So there are other approaches than the ones I described. One is continual learning, which retains lifelong features. We've done some work in the space. We're looking at it as well also. This issue of explainable modeling, looking at the causality underlying the reason. So this has been a hot topic in the machine learning literature for a while, and I think it has some applications here. So if we want AI native networks, we must go towards generalizable frameworks. Again, call it whatever you want, brain or whatever you'd like to call it. Now, if you, there was in my first slide, I talked about the flip side of the coin, not using learning to improve wireless, but actually using wireless to support learning. So I'm going to talk a little bit about that. This is based on our work with Mingje as well, a TWC paper from last year. So the idea is in federated learning, the main idea of federated learning is to train the network or train the neural network in a distributed way, where you have multiple devices, they own their own neural network, they transmit weight parameters to a central base station, and then they can together converge to a neural network model they like without having to have a central controller controlling everything. Now, in the machine learning literature, for a long time, they were interested in questions like architectural questions, privacy questions, even some sort of reducing the weights like communication efficiency question. But they were never interested in seeing how an actual system, like a cellular system, will impact the accuracy of learning, because here you're relying on the wireless channel, which we know has fading, has errors, has many issues, has delays, has energy aspects that will affect these Ws. What happens? So the question we ask was very fundamental here. What happens if these Ws are subject to a real wireless channel? How it happens to the machine learning aspect? So looking at it here again, wireless errors will impact the FL performance. Delays in energy consumption will impact the FL performance. What we did is we reformulated the problem as a problem of allocating, selecting users, allocating transmission power to those users in a way to optimize the accuracy. This is what I call joint wireless ML design. I think it has become a little bit more widespread nowadays, this term of joint ML and wireless. And we started this in this work where we said, well, I'm now controlling an accuracy function, which is a machine learning function, not only through the samples and the weights, which is what machine learning people do, but also through the wireless network, because I know that the wireless network impacts the FL. And we showed mathematically in a very fundamental result here that the convergence of federated learning now depends on this term. And this term comes from the QI, which is the packet errors. So packet errors, I don't know if I don't have the term, but this is packet errors. QI is packet errors, RI is resource blocks, PI is the power, and A is a small number between 0 and 1. Without wireless, so going to every single FL paper before our work, you would always converge because you have this term, take T to infinity, A is less than 1, this will converge. Unfortunately, with wireless, you have this term, and you need to minimize this term so that FL works well. This goes back to joint design, right? I need to minimize the impact of wireless here so that federated learning actually converges. This was for a full gradient descent, but you can do it for stochastic gradient descent as well. So I can show one slide only on how we improve identification accuracy. We had 3 baseline. Baseline C was a very random heuristic. Baseline B was Google's algorithm. And baseline A was one that optimizes only the power, not the resource, not the user selection. We can see we're much better. I mean, we have a better accuracy just by being wireless aware. Now, taking this a step further, and I think this is where, if for those interested in FL as a 3GPP use case, this is a step further. Can we look at this trade-off between energy, precision, and accuracy? What do I mean by that? What I mean is that existing FL, they use full neural networks. Those are computationally very heavy. I can use quantized neural networks. Those are computationally less heavy, but their precision is less. So, but they require less energy, and our devices are energy sensitive. So how can we tweak this? How can I choose the number, the precision level of my quantized network to maintain good energy efficiency and to also maintain good accuracy. You can see this very interesting figure. You have the accuracy of your learning, you have the level of precision of your neural network, and you have the energy consumption of your system, including the transmission energy as well. So you can see there's a very interesting trade-off. You have you want more accuracy here. Look at how energy blows up and how many how much precision you want. You want to strike a balance. This seems like a good place. And you can see that by understanding this trade-off, you can optimize it. And this is what I show here, where we show that our model does better in terms of energy because he's aware of how to optimize the architecture. So fundamental question for you all to think about here, forget federated learning, think about what is the optimal distributed machine learning algorithm I can implement over a wireless network that can execute a task I want, let's say semantic communication or something of that sort, while minimizing energy and being accurate as well. So that's kind of like a big question. So you can see we have a lot of works on ML. You can check, we have on federated learning as well. So I'm not gonna dwell too much here. Concluding with an overview of our work. So we have many thrusts. One of them is everything 6G, right? So we started this work a long time ago and it's evolving from the reliable things I discussed today to terahertz and RPSs to AI-enabled XR and digital twins. Of course, semantic communications, which is now, the equivalent of AI in the past. In the past, whatever paper you write, you should call it AI. No, whatever paper you write now, you should call it semantic. And I think that's a little bit becoming a little bit too much. But what I'm saying here is in looking at semantic communication, meaning understanding the meaning underlying information in order to go beyond Shannon's bits and bit error rate is something important. And we've been looking at it. You can see I hinted a little bit at it when I'm talking about generalizable AI, because you need that to make semantic works. We've been doing quite a bit at the intersection of control and communication, and in general, designing ML algorithms with wireless and networking in mind, of course. And we've been doing quite a bit on information. So we were looking at age, now we're looking at semantic. I have a few students recently starting to look more on quantum networks. There's a lot of things we can do there as communication systems. And I have a few projects that are more implementation related to kind of smart cities. And I've always done game theory, which gives foundations to a lot of things that I discussed today. So distributed learning is an exciting area. It's merged with wireless. Remember, it's not just federated learning. In my opinion, federated learning is outdated by now. It has some use cases, but I think we've done quite a bit in it. Think more about distributed RL in the sense of being generalizable multi-agent systems. And in some sense, if I want to add adjectives, I would say augmentation, multitask, continual, and explainable AI. And there's a lot of applications from semantic to other things. And with that, I conclude the talk, and I'm happy to answer questions.
Thank you so much, Walid, for these nice insights on the use cases. Well, you can see that there's so much that you can do with GANs and how federated learning or distributed learning can do. So now we are going into the Q&A. And of course, I would like to also inform participants that are watching us on the neural network that you can type your questions on the video wall, and then we'll take them during this Q&A, or we can answer them during the networking session. Now, I would like to welcome Vishnu, my colleague, to take over for the discussion or the Q&A session. So over to you, Vishnu.
Thank you so much, Thomas, and excellent talk, Walid. I think you really touched a lot of aspects, and I agree with you that typically when we say distributed, we think about federated learning, but you have really enhanced my thinking, at least, and I'm sure I got several messages while I was listening to you. There are several messages from students who tells me that this is absolutely brilliant. So my question is about, you told about wireless aware federated learning. I think this is a very exciting area. There has been some initial studies, but nothing close to what you described. You basically took it apart and described it very nicely. My question is a little bit tangential. I want to ask you, with these new architectures in wireless coming up, there is a lot of focus on exposure. You mentioned about 3GPP use case. There is a lot of talk about disaggregation and so on. So what is that we can help from a wireless point of view? What is your wish list? So let's say if you put the cap of, if you wear the hat of a machine learning part, right? What would be your wish list top, let's say the top things that you would need from the architecture, you need from the wireless side, so that we can make your life easier? Is there anything like that?
I think this is an excellent question. And I think the first, probably on top of that wish list, is a communication channel that can faithfully convey whatever I am transmitting, whether it's a weight or, I mean, of course, there's many more advanced architectures now. So a faithful bit end-to-end transmission of information that is, I mean, for lack of a better word, I would say reliable, but not in the 3GPP reliable sense only. It's just being reliable, right, in the English sense. And I think that's on top of it, on top of the wish list. Second is being energy efficient in the way the system operates, because now when I deploy these architectures, the devices will use computing and communication. So energy becomes critical, right? I can't communicate. If communication will take more energy than doing the computing, it's a problem, right? So tweaking, basically coupling the two is important. And number three, I would say, as wireless people, we've always designed application-aware protocols, right? So we need an AI-aware protocol, right? Not just AI native, which is the other side of the coin, but actually maybe AI native, AI aware, right? It is based on AI, and we've done that. I mean, we used artificial neural networks to optimize how we use federated learning, right? So somewhat of again, AI aware protocol in the general sense.
Thank you so much. About your top points, you had about latency, right? I think you had some, I should say, very interesting results about your studies on latency, especially applying these techniques of GAN. Especially you called it brainstorming GAN, so sharing experience, etc. Those are the words that you are using. Could you tell us, or for the benefit of the students and the learners who are listening, could you tell us once again your results from the latency side of point of view?
Yeah.
I think you had around slide 31 or 34, around that, around those slides you had the results. Yeah.
I think it's here. I think there were two of them. I think this one and okay. Let me start with the first one. It was centralized, but still, I think this one is important. So I think one of the things in latency, so if we want to kind of break down latency, we have, of course, our networking latency, which includes queuing, includes transmission time, and all sorts of processing. Of course, transmission time, we can more or less control it. The more we have, more bandwidth or things like that. But you still have computing and other things. The issue is when you go towards AI, it's very natural, and I don't fault us as a community to rely on reinforcement learning, because it is very natural and it makes a lot of sense. The problem with it is it has been designed for systems that don't need latency. They don't, in the sense, they don't need to react very quickly. One would argue maybe autonomous vehicles need, but that's why we don't have autonomous vehicle yet, because we don't have the actual latency needs. But so what I wanted to focus on in that particular aspect is this transient period, the period where RL is very good at learning, but it needs time. And we as wireless have been ignoring that time. And we can't if we are looking for low latency communication. Because then during this, 50 epochs is not an insignificant time. So our goal has been to try to reduce this latency, which in more technical terms relate to the RL sample efficiency. Now, there are different ways to do it. One way is to use GAN as experience. Another way is the use of meta-RL as a way to learn a class of problems. And brainstorming GAN is just a distributed version. So, I think you were referring to this one here, the probability of convergence. So here, the way we do it is we optimize how often you actually exchange information in a way to minimize the latency, which is again the probability of converging to your neural network. So the bottom line being here is you plug in AI. Yes, it gives you intelligence. Yes, it gives you all sorts of brain functions. But just like the brain, it's slow to react in many cases, right? So sometimes it's just cannot react quickly. So we need to work on that portion of the latency, which is being introduced by us because we want to use AI. Now, I've seen some work, I think, by Jacob Hoydis and some of the others at NVIDIA, where they argued, well, let's not use RL, let's use Bayesian optimization. Unfortunately, Bayesian optimization is not as good in the problems we deal with as RL. Even though it can be faster, there is a point to be given to it. But I would still think that designing better reinforcement learning algorithms is the way to go. And you have to play on RL. And we recently looked at a different, kind of a different idea. I didn't present it. We don't have final results yet, but the idea was this one. Let's say you have two RL, which are two MDPs essentially, looking at different problems. What if there are a sub-problem of a bigger problem we can call a super environment? Like, let's say you have a baby crawling on wooden floor and a baby crawling on a carpet. These are related tasks, but they're not quite the same. Can we solve one and then do better with the second by creating a new task called a super task called flooring, rather than wood? And so it's a general task that can specialize. We've done some work in that space, but I don't have wireless relevance yet. I have the relevance, but I don't have wireless results yet. But that's one promising angle.
Thank you so much. I think another question which was coming is about learning the distribution of tasks. You did mention that, and
Yes.
I think you just now talked about that as well. That's a very interesting concept. Actually, I have not heard that before. It's a quite interesting concept. Could you tell us what are the key enablers for that? What as machine learning students, machine learning engineers, what are the key aspects for this particular aspect that you brought out today?
That's a really great question, and that's an interesting area. So one of the most, let's say, established now techniques to be able to learn let's say a group of tasks or a distribution of tasks is the concept of meta learning. So meta learning is the idea of, I mean, they call it learning to learn, which is essentially learning, not only optimizing, not only training your neural networks, but also training the parameters you use to train the neural networks. And that's exactly how it allows you to actually learn more tasks. Now, it has been done. I mean, I think there's a few groups in Stanford and so on who have done interesting and amazing work there in the machine learning community, but their interest is different of ours in the sense that they're not looking at an RL environment. So what we did here is we actually leveraged the idea of meta learning, but in the context of reinforcement learning of this trajectory problem. That is one way. The other way is to look at some of those, like, again, for lack of a better term, reasoning aspects of learning, which means that there are some techniques like causality, where you can identify relationships between different learning tasks. And those relationships can be built and then allow you to actually generalize. The third aspect would be what I mentioned early on, which is creating super environments, super general problems, which if you solve them, they can actually specialize in other tasks. I would say this is a hot area. There's no direct answer. Perhaps the most established field would be meta-RL or meta-learning in general. There's also a fourth one I forgot, which we're looking at now as well, which is continual learning. Continual learning is like this, also known as lifelong learning. It's the same, actually, two terms for the same thing, which is essentially the idea that learning is a gradual, lifelong process, which means that you keep history of what you learn. And from that history, you can learn groups, because you're kind of learning the concepts one by one in some sense. But I think that's a great area. I don't think, in my opinion, there's very rare serious work on that in communications yet. There's very great works in NeurIPS and those venues, but not in our venues yet.
Excellent. I think we are hearing some very, very important keywords. Thank you so much. I believe we should be be waiting for more results from you in this area. And
Yes.
I think as you correctly mentioned, there is a lot of talk on semantics and the semantic communications, but I think we should be focusing more on these lines, which will get us more benefits. I think from a machine learning point of view, yeah.
I think I think the issue of semantics is very important, and extracting meaning and transmitting it is very important. But I think it's a means to an end, and seeing our community making it an end, being like, oh, the system will be just semantics. But no, I want a system that can serve these different things, and I would use semantics as part of a bigger picture. That's kind of the point.
Yes, yeah, exactly. I want to ask one last question, because I think this can kind of lead us to more discussion. I know there may be a lot of discussion in the forums of ITU neural network. We have actually a forum. So we with this kind of questions, I would like the community to engage a little bit more. You did talk about quality of data, but indirectly, I mean, this is what you meant, I think, when you told about wireless links and its impact upon machine learning. I want to ask about the similar question, but in the context of generating data. So just like what you mentioned about this impact of wireless, or you called it wireless aware, right? Similarly, is there a constraint, or is there a problem that you see in generating data, which may be quality wise, or something that you need to take care or worry about with respect to the quality of data that is generated? And when it comes to addressing exactly the point that you mentioned, unseen tasks. So this is the important point that you mentioned, how to handle unseen tasks. So when addressing that point, does the GANs work well with respect to generating quality data? That's my question.
That's a great question. I think the short answer is generating quality data is the holy grail still for everybody, right? So I think our approach to that part should be multi-pronged. GAN is one way, and I have to kind of also acknowledge that the GAN community has done incredibly well to have very advanced GAN architecture. So in my work, I relied on the original Goodfellow, but you can plug in any other one, right? It's just, my interest was in the distributed aspect, not in the quality of the GAN itself. But I think they've done quite a bit. So there are, I mean, I lost track of the number of abbreviations on InfoGAN, CGAN, DGAN, and all that stuff, but they're really good. So they've done quite well, but it's still, the thing is, we want it to be, in wireless, our real data is, even if you have access to it, you cannot have access to exactly what you want and to all what you want at all times. So our approach should be multi-pronged. One is, GAN is one way to augment the data, but of course, we all acknowledge that's not enough. On top of that, we need faithful simulators, right? To make sure that what we're training on is good and so on. Third, we need to have a little bit more fundamentals on the AI side, right? So how can we control more and more of the AI algorithm itself? Because if I can have theoretical analysis of that, I can have some guarantees which may not be data dependent. So I mentioned in the first slide nearly training free, because I know we're never going to be training free, but being as close as possible to kind of reduce the reliance on training. There has been some work we're looking at it. Hopefully soon, within a couple of months or so, we'll have something on that. The idea of combining the power of neural networks, which are biased towards data, and the power of traditional AI, which is called symbolic AI, which is really strong in actually generalization. And people forgot that because it was no longer relevant with deep learning. But now we're remembering that deep learning is so data biased. So we need to go back to the original artificial intelligence and see if we can combine the two. And the AI community is looking at it, but again, their problems are not like ours. So I think these three aspects are ways to confront that: augment the data, use GAN, have theoretical designs that are wireless centric. That could be through Meta. I mean, I think we're creative enough. There will be a lot of approaches. And third, have faithful simulators. And I think that's where industry and some of the more practical partners can help us, say this is a faithful environment that can give you data, or you can test your data on.
Thank you so much. Excellent. I think these are three gems, I should say, which we take out of your talk. Exactly, you really brought them out very clearly, especially the faithful simulators. You call it faithful simulators. Very interesting. And yeah, I think we should, we would like to engage the community, especially with respect to these points that you brought out.
Yeah.
I want to request to continue this discussion in the neural network. Thomas is here. He can explain how to do that. And thank you so much for patiently answering all the questions. Yeah.
Thank you.
Thank you so much, Vishnu. This is the end of the Q&A session, and I would like to take this opportunity to thank our lead for making time to do this great presentation. We learned a lot how we can use GANS in wireless communications, federated learning, and many different topics. I think this is going to drive research in future networks. At this point in time, I would like to thank everyone for joining. We are not finishing the session. We're just finishing this webinar part. Now it's time for networking. So we are going to join into the neural network. Let's network, chat, interact for the next 30 minutes. So I'll see you in the neural network, and I would like to ask my colleague to take over for the closing information.
All right, thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.